Nicole first.
Nicole is first, yeah, we already checked.
As it rolled off last time. I'm not sure if that was that time.
We are waiting a couple of more minutes. There are people coming in from lunch, so just a couple of minutes. Okay. Well, good afternoon. Thank you and welcome to this second session about star formation and disk. We'll start the session with a presentation by Nicole Arulanantam, who will tell us about an edge on disk observed with Miri. And let's see if we can start it here. Does it work? I hope it does. Yes, the floor is yours. Thank you, Nicole.
Okay, can you hear me okay? Okay, awesome. So I'm Nicole Arulanantham, and I am a postdoc here at STSCI working on star and planet formation with JWST. And today I'm going to show you some results from a project where we're using the Miri MRS to observe an edge-on protoplanetary disk. So for the people in the room who might not spend a lot of time thinking about planet formation, I wanted to start with this illustration of what we think the planet-forming environment might look like around a young stellar object. So we have our YSO at the center here, and then we have this beautiful flared protoplanetary disk of dust and ice and gas. Now, if we look over here on the right-hand side, we'll see this scale bar that marks off the radial distance from the YSO and AU. And we see this kind of distribution of wavelength regimes that we need to study the disks. And so what I'm going to focus on today is this mid-infrared region where temperatures within the disk itself are not too hot, not too cold, they're just warm enough that the emission is detectable with Miri. And so you'll notice on this scale bar that we are sensitive to emission that's coming from inside about 10 AU. Now at the distance to our favorite protoplanetary disks, this is well inside the pixel scale of even the channel 1 detectors on Miri. So we don't necessarily expect that we're going to spatially resolve any of the emission directly from this region. Now, when we look at cartoons of protoplanetary disks, there's a reason why we see them usually from this nice edge-on view with a slice through the middle. And it's because when you look at a disk edge-on, you can use a combination of different observational tracers to map the material in the disk from the very warm surface layers where we see warm gas, down to the disk midplane where we'll see ices and more solid material that will actually form planets in the midplane of this disk. So with this in mind, Melissa McClure designed a very nice Cycle 1 GEO program to observe icy dust and gas in protoplanetary disks with both NIRSpec and Miri. And this is the target that I'm going to talk about today. This is a really nice HST image, and the white band here shows the ALMA observations of this disk. And you'll see that with HST at optical wavelengths, we have this very nice dark midplane, and so the disk itself is very optically thick here, and it's masking the light from this central YSO. And the ALMA dust continuum emission is coming from much colder dust, and so that's sitting right in that midplane. And then we see these two really beautiful lobes of scattered light from the disk. And so these are small grains in the disk that are forward scattering light from the star, and we see this beautiful butterfly shape. In addition to these beautiful scattered light images, these targets were also observed with Spitzer. And so this is an example of what the 1D spectrum might look like. And we can see these signatures of water ice, and so this is something that really should be a slam dunk if you look at it with JWST, right? If you have a tiny Spitzer water ice, and if you have a water ice not with JWST, it's really going to be booming when you look with this beautiful new facility. Now, this is the last 1D spectrum that I'm going to show you for the rest of the talk. For the rest of the time, I'm going to focus on images that we've made from the 3D spectral cube. So this is work that is very close to being submitted, so I ask that you please not take any photos or share it outside this conference. So this is what our disk looks like in the Miri MRS spectral cube. So you'll notice that this ALMA dust continuum emission it looks much larger. And this is just because the scattered light lobes of the disk are much smaller at mid-infrared wavelengths, which is what we expected. And so this is what the dust continuum the scattered light from the dust looks like at 5 microns. And if we go out to about 17 microns, we see something very similar. You'll notice that this looks much blurrier, and this is just because the pixel scale is much larger when we go out to longer wavelengths. But we see the same kind of butterfly pattern from the two disk lobes and this nice dark midplane where the ALMA contours sit very nicely. Okay, so this is what the dust is doing at 2 different wavelengths, but of course there is a lot more wavelength space in those cubes from the Miri MRS. And so in the process of flipping through the cube, we found some very unexpected and exciting things. We're also seeing spatially extended gas phase emission from this protoplanetary disk. We'll just leave these up here for a minute for everybody to absorb. And we'll step through these one by one. So in this upper right panel here, we're looking at the dust continuum near 17 microns. So this is very similar to that image that I showed on the previous slide, but now it's just green. And then down in the bottom right here, we're seeing 2 lobes of water emission. So this is emission that's coming from the rotational lines of water. And in the bottom left here, we see this very spatially extended emission from H2, and this is the S1 emission line at 17 microns. And so the scale of these images is quite large, right? We would not expect to be spatially resolving this emission with the MRS. But what's happening is that we actually have dust on the surface of the disk that's taking those gas phase emission lines generated in the inner disk and scattering the light out to larger radii. And so we're basically seeing the inner disk conditions projected out to larger radii. But when we compare the distributions here in this 3-color image, if we stack the dust, the water, and the H2 on top of each other, we see that across the disk itself, there's a lot of white here corresponding to where the three different emission features overlap. But we see a lot of red sticking out, so something else is clearly going on with the H2. So to explore which spaxels have significant H2 emission but not much of anything else, we produced these difference maps. And so to do this, we basically normalized the dust images at 17 and 5 microns by their peak surface brightness. And we also normalized the CO and the H2 images at their peak surface brightness, and we subtracted the normalized dust from the normalized gas. And so when you do that, for CO, you see this pretty random map. There's not really a pattern to the spaxels, so we can tell that there aren't really regions where we see CO, but not dust. So again, this is very consistent with population of dust that's scattering the CO. But when we look at the H2 image, we see something very different, right? We see this very beautiful, spatially extended X that's sticking up above the dust contours that are shown here in white. And if we measure the angle of each of these little V shapes that together form the X, we see that that has an opening angle of about 71 degrees. And this is very consistent with what models predict disk winds to look like. And so with the Miri MRS, we've captured this disk wind, and we are actively seeing this disk in the act of dispersing, which we know when we remove material from the disk, this is what sets the upper limit on the timescales for planet formation. Okay, so again, I've only shown you two different sets of emission lines. There's a lot more cube to look at. And so this is a composite image of what some of the molecular gas emission lines look like at shorter wavelengths. So in the upper right corner here, again, we're looking at the CO emission from the rho vibrational lines around 5 microns. In the bottom right here, we're looking at the rho vibrational water emission lines. And over here in red, we're looking at the H2 emission from the S7 transition. And so we can see that we're not seeing as much of the spatially extended H2 emission at these shorter wavelengths. You'll also notice that it looks like the dark midplane of the disk is better resolved, but again, this is just because the pixel scale is so much smaller in channel 1 compared to channel 3. And when we look at the composite image, we start to see some interesting structure. Did anybody notice anything looking at these images? Did anybody notice anything unusual about the H2 or the water? You can just raise your hand. I'm not going to make you say what it was. Yeah, there's definitely some weird stuff going on here. So first thing, we start to see a little bit of water that's sticking up at the bottom end of this fainter lobe. So that's weird, right? There's no H2 or CO there, but there's still a little bit of water. And all three of these emission lines are shown at similar spatial resolution. And you'll also notice when we look at the H2 that this side of the disk is actually brighter. And this is something that we see in all of the H2 emission lines, actually. So even if we look at the S1 image that's dominated by this really beautiful wind structure, we see these kind of blobs in the lower quadrants of the disk. And so to get a sense of what might be happening here, we did a couple of different just quick checks. So first, on the left-hand side here, we produced a temperature map. And so this was done by computing a rotation diagram per spaxel for the 3 H2 emission lines that are observed in channel 1. And so when we do this, we can see this kind of hot spot here corresponding to a much hotter temperature. So this is around 1300 Kelvin. We also see, this is pretty cool, we see these kind of cool regions here where in the S1 image you actually see the base of that X wind. And so we're clearly seeing some brightness asymmetry here that would correspond to a hot spot. But if we calculate a velocity moment map, which I'm showing here on the right-hand side, we don't really see any spectrally resolved structure here. So the red spaxels in this image correspond to redder positive velocities, and the blue ones correspond to more negative velocities. And you'll see that everything kind of bops around between plus or minus 10 kilometers per second. And so at the spectral resolution of Miri, we're not seeing any kind of disk rotation. So this is clearly some kind of significant brightness asymmetry. So what we think is happening is that instead of having this really nice class 2 disk with no weird structure, what we think is happening is that the inner disk has become misaligned. And we can actually measure this by looking at the tilt of the jet emission that we resolve in the images with respect to the gas emission lines. And so if we have a very slightly misaligned inner disk, this would cause more forward scattered light to come from this lower right quadrant of the disk. And the back part of this misaligned disk will forward scatter some more flux into this fainter lobe. And we're really seeing this nicely in the H2 emission lines that extend a little bit more out from the scattering surface than the CO and the water. So I think I'm just about out of time, so I'll come to my conclusions. It turns out that the Miri MRS can be a really powerful tool for mapping protoplanetary disk winds if you have the right geometry and a big enough disk. We are also seeing really nice scattering of emission lines from warm gas, and so this is something that we really need to take into account when we're thinking about the composition of the inner disk as probed by the Miri MRS. And we're also able to resolve brightness asymmetries across the disk, and so this could be a really nice way to detect signatures of inner disk substructure that we wouldn't otherwise be able to spatially resolve. So we are just about ready to submit this work, so please stay tuned for these and other exciting results from the MIDAS team. Thank you.
Thank you very much, Nicole. This is very exciting. I'm sure there will be questions for you. Yeah, I already see some hands sticking up, so, well, let's start from here.
Hi, Laura Flagg, Cornell University. Is there a way to quantify how much mass is being lost in the disk winds with the H2?
There is. So if we assume that this emission is optically thin, we can derive a mass from the H2S1 line of approximately 10 to the minus 10 solar masses. And that's also assuming a temperature of about 100 Kelvin. And so if we assume a typical disk wind speed of about 10 kilometers per second, which is what we get from the models, this comes out to a mass flux of about 5 times 10 to the minus 9 solar masses per year.
Super cool, thank you.
There was, sorry. Oh, there was one there. Yeah, go there, go there. You're closer.
Hi, John Debus, Space Telescope. So for that misaligned inner disk, can you constrain how much of a misalignment there is?
Yes, so if we measure, forgot to say this, we also see spatially resolved emission lines from a jet. And so if we come back here and look at the axis of this iron 2 jet, we see that it's slightly tilted with respect to the plane of the disk. And so we can measure a very slight inclination angle here of about 2.5, 3 degrees. So it's very slightly misaligned.
Yeah. Mason Ruby, University of Memphis. Yeah, thanks. Great talk. I was just wondering if you have any guess as to what's causing the warped or misaligned disk. I know sometimes you can have binary systems that can cause that, or external gravitational perturbations.
Yeah, so there are a lot of things that can cause your inner disk to become misaligned. Like you said, one of the popular methods is if you have a binary that causes some torque on the disk and causes it to break, and then your inner disk can become tilted. The other possible mechanism is if you have a planet there, but it kind of becomes a chicken and an egg problem, where do you have a misaligned planet that's shepherding the outer edge of this disk, or, it's hard to tell whether the planet came first or whether the misaligned disk came first. But it'll be interesting to explore, especially if we see more of these with Miri.
Thank you very much. Sorry there is no more time, but you can ask Nicole later on during the coffee break. Let's thank her once again. Thank you very much. And now we move to the next speaker, who is Nana Majaj. And let's see if I'm smart enough to work with this. Let's see. And let's make sure that we have your version. It's this one. And this.
Perfect.
I think so. There you go.
Am I audible in the back? Yeah, perfect. Okay. Hello, everyone. I am Naman Bajaj. I'm a second-year graduate student at Lunar and Planetary Laboratory, University of Arizona. I'm working with Dr. Ilaria Pascucci, and today I'll be presenting some results from our JWST project titled Discovery of a Spatially Resolved Disk Wind using JWST Miri MRS, that is mid-resolution spectroscopy. This work would not be possible without significant contributions from the many people mentioned here. So, according to the classic picture of protoplanetary disk evolution, the disk material in the inner disk is accreted via viscous accretion, and the gas in the outer regions is dispersed through photoevaporation. Now, after a few million years, the accretion rate falls below the photoevaporative wind mass loss rate, and this can create a gap in the disk. Now, this stage of a protoplanetary disk, where there's a large gap in the dust of the disk, is called a transition disk. And immediately after a few 100,000 years, photoevaporation dominates and quickly disperses all the gas in the disk. Now, this photoevaporation can be traced in ions of atoms, such as neon and argon, because for the reason that they're available at the surface of the protoplanetary disk, and they do not deplete with time since they are noble. So this is the classic picture that we have about protoplanetary disk evolution. But more recently, instead of viscous accretion, MHD or magnetohydrodynamic disk winds have gained attraction due to their observations, and they are believed to drive accretion in the disk by removing the angular momentum from the disk. So do we have observational evidence for this whole picture, the whole very nice picture that we have here of the evolution of the disk? The answer obviously is no. So for photoevaporative winds, we have very strong neon-2 line detections. And these line detections using ground-based high-resolution spectroscopy have shown a consistent blue shift of about 5 to 20 kilometers per second and modish widths of 15 to 40 kilometers per second. Now, this is consistent with the wind because jets eject at speeds around 100 kilometers per second. So this says that neon-2 is tracing a slow wind. And the red line in this plot right here traces the photoevaporative wind model predictions. So this looks good, but the problem is just based on the spectral information, we cannot exclude the possibility of MHT disk winds or neon-2 line tracing those MHT disk winds. So is neon-2 tracing MHT disk winds or photoevaporative disk winds? Because that will determine, is it driving the accretion, or is it a tracer for the accretion, or is it a tracer for the photoevaporative winds or the dispersal of the disk? So to try to solve this problem, we observed Teacher. Teacher is a T Tauri star. It is at about 100 parsec. The estimated age of Teacher, it has a large range in literature, but it's older than 2 million years. Teacher has a blue shifted neon-2 emission of about 10 to 15 kilometers per second. And this is important because we do not see the red shifted component of this neon-2 emission, which means that there is something in between which is blocking our view of the red shifted component of the wind, because the wind, as Nicole just showed very beautifully, we can see it in both the lobes or both the sides of the disk. So there is something that is blocking our red shifted, our view of the red shifted component. So there has to be a dust in the mid plane where we are seeing this wind, which can block the red shifted component then. And Teacher has a very interesting structure. So it has a very small inner disk of size less than 1 AU, a large dust cap of 20-25 AU, and then an outer disk, as you can see in the ALMA image, an outer disk of about 20 to 30 AU. Now, photoevaporative disk winds in Teacher cannot be driven from the inner disk because it is too deep into the gravitational potential well of the star for the gas to escape. And since we know there should be dust in the midplane, it means that if neon-2 is tracing photoevaporative disk winds, then it has to go over the outer disk, which is at about 20 to 30 AU. And if neon-2 is tracing that wind, then we should be able to resolve it with Miri MRS. But if we do not resolve this emission, this neon-2 emission with Teacher, then that would mean that it is actually tracing MHT disk winds and not photoevaporative disk winds. So that is the hypothesis that we have here. Teacher has a disk inclination of 70 degrees, so almost an edge-on disk, and a position angle of 113 degrees calculated from the north. Teacher was observed under the proposal 2260 led by Professor Ilaria Pascucci. It was observed on August 13-14, that is a day before I started my graduate school. It was observed for about 4.5 hours, and we also observed a dedicated background in the exact same settings as Teacher. Teacher was observed with Miri MRS, that is in the IFU mode. That is, we have both the spectral and the spatial information at the same time. So to calibrate the observation, we calibrate the source and the background observations individually. And once we have the IFU cubes from source as well as background, that is when we perform the pixel by pixel background subtraction. And we found this method to work better than most of the methods suggested in the pipeline. And then we extract a spectrum from the IFU cube of teacher. And this is what the spectrum looks like. So for the first time, we have not just 1 or 2 or 3, but actually 4 forbidden noble ionic lines, which are possibly tracing disquins because we know neon 2 is tracing disquins. So we have argon 2, argon 3, neon 2, and neon 3. This is also the first ever detection of argon 3 in a protoplanetary disk. And along with that, we have several polycyclic aromatic hydrocarbon features that we heard so much about yesterday. And except for that, there is nothing else, and just one H2 line. So once we have these forbidden lines, what we can do is we can use the ratio of the line intensities of these lines to know more about the energy of the photons that are driving the ionization in the disk. So we use the neon 2 by neon 3 ratio and neon 2 by argon 2 ratio. The model predictions are from Hollenbeck and Gorty back in 2009. So if you look at the neon 2 by neon 3 ratio, you can see that all the data points that we have, most of them are lower limits, except for 2 points in literature and 1 teacher from this work. All of them very strongly exclude the hard EUV model. Hard EUV is essentially EUV, it's a spectrum where there are more photons with energy above 41 electron volts than below 41 electron volts. And soft EUV is where you have more photons with energy less than 41 electron volts than above. So we can very strongly exclude the hard EUV model here. And if we look at the neon 2 by argon 2 ratio, then we cannot really exclude the hard X-rays model for all the disks, but at least for teacher from this work and one other source in literature, we can exclude the hard X-ray model. So this suggests that soft X-rays or soft EUV are driving the ionization of the surface of this disk in teacher. And since our goal was to see whether this is spatially resolved or not, we perform continuum subtraction. So this is an example of how we do the continuum subtraction. So you have the original spectrum in red, you fit a polynomial shown here in blue to the continuum, and then you subtract this polynomial from the original spectrum to get a continuum subtracted spectrum in black. But this is something then we do for each spexel or each pixel in the IFU cube of teacher. Once we have these continuum subtracted maps, we also perform PSF subtraction to see to compare with the PSF. If it's bigger than the PSF, then we have resolved this emission. If it's the size of the PSF, then we have not resolved this emission. So to do the PSF subtraction, we take the PSF, we take this continuum subtracted line maps, and we fit the centroids to both of them. We shift these centroids to the center of the image. We scale the PSF to the line emission, and then subtract the PSF. And this is what we get. So on the upper panel is PSF subtracted continuum at 12.8 micron and PSF subtracted neon 2 emission. And on the lower panel, we have PSF subtracted continuum emission at 7 micron and PSF subtracted argon 2 emission. And it is very clear that both the continuum and neon 2 emission at 12.8 micron are spatially resolved. And what is also very interesting to see is if you look at the direction in which the continuum is resolved, that is this direction, and in the direction in which neon 2 is resolved, that is this direction. So you see that neon 2 is actually tracing emission away from the disk, and it does not have the same position angle as that of the disk. And very interestingly, we see that argon 2 is not resolved and rather shows a much more compact emission. Now, what can we learn? We know that the hypothesis was whether neon 2 is extended or not, but we can learn more because now we also have spatial information on argon 2. So Andrew Selleck, who is now joining Leiden University, is modeling these winds, and what he finds is for the low mass loss rates of the order of 10 to the power minus 9, and so that is the mass loss rate, and if you look, Rn is essentially the wind launch radii, so at which radii the winch is being launched at. So for none of these, we see a we see a significant difference in the spatial extent of neon 2 and argon 2. But if you increase the wind mass loss rate to 10 to the power minus 8, and if you look at the very close-in winds, then you start seeing that difference. You start seeing that argon 2 is much more compact than neon 2. So this suggests that the wind mass loss rate in Teacher is quite high. That is, it is dispersing the disk really quick. And the launch radii of this disk winds is very close in at about 1.5 or 2 AU. For more work, for more details on this work, he will be writing a paper on this, so look forward to that. Another thing that we observe in Teacher is the infrared variability that we were not expecting. So in gray here is the Spitzer spectrum taken 17 years ago, and in blue is the JWST spectrum, and we see this kind of a seesaw infrared variability. Teacher has been known to show very large optical variability, and Chenny and Shi at University of Arizona is trying to understand what this variability tells us about the disk and what is causing this. So he can reproduce this IR variability through two methods. One is reduction in the inner disk mass, but that does not give you the optical variability. So an inner warped disk, which has reduced significant mass in 17 years, is what the model is what can explain both the phenomena very well, and as shown is in this toy model. So for more details, look forward to a paper by Chenny and Shi as well. In summary, we have the first ever detection of argon 3 in a disk, and we have also the first ever detection of all these 4 lines possibly tracing disk winds in the same disk, which says JWST Miri MRS can be successfully used to study disk winds and understand the problems that we want to solve. The line ratios add significant constraints, and we find that soft X-rays or soft EUV are driving the ionization of these winds. And continuum and PSF subtracted map shows that neon 2 is spatially extended, but argon 2 is not. Extended neon 2 emission confirms that it is in a spatially extended disk wind, and it is still consistent with photoevaporative disk wind models. And that will be my summary. Thank you so much.
Thank you very much, Naman. Questions? Let's see. Is there anything online? No questions online. Let's see in the room. Yeah, Kieran.
Hi, Kieran Rogers, Leiden University. So you were trying to work out what the excitation mechanism was and what the energy of the photons was, and you came to the soft X-ray or extreme UV. Where did those photons come from? Is that from accretion or from the accretion flow?
Yeah, the chromosphere and the accretion shock.
And do you have an estimate for the actual, say, amount of soft X-ray or EUV? Because that could then be an accretion luminosity tracer.
Yeah, so it is very hard, or rather almost impossible to calculate the EUV luminosities. So there is an upper limit, and the luminosity of EUV needed to excite these atoms is below the upper limit that we have for Teacher. So it is still possible that we have soft EUV here.
Okay, thank you.
Thank you very much. More questions from the audience? Oh, yeah.
Nicolas Flaget from Space Telescope. When you subtract the PSF, where did you get the PSF from?
It's basically standard stars. We take 2 different standard stars. So yeah, I also have, so that was a result that we have from one of the standard stars, but we see that it is not very well resolved. It is actually barely resolved. So we also do the same thing with another standard star, which was actually observed right after Teacher. It was not a part of our proposal, but it was somehow observed right after Teacher. So we get the exact same results.
One final quick question, if there is one. Has anything come up from the online? No? Well, then let's thank Anand once again for his presentation. Thank you very much. And we move to the next speaker, who is Sierra Grant. And let's see, Sierra, please come in, and we try to load your presentation. I hope you had a chance to see before whether it was fine.
Yes.
Good. And here it is. And there we go. Yes. And that's for you. Thank you so much. I'll give you 2 minutes.
Thank you. Can you hear me well in the room? Hopefully online as well. So hello everyone, my name is Sierra Grant and I'm a postdoc at the Max Planck Institute for Extraterrestrial Physics. And today I'm going to be talking about studying gas and protoplanetary disks using Miri. And this is work done from the Miri Mid-Infrared Disk Survey team, or the MINDS team. So, just to place ourselves into the context of star formation here, my previous speakers did an excellent job of placing us in context here. But we're starting from our prestellar core. We're collapsing to form a protostar and a protostellar disk. We have our protoplanetary disk that is then actively forming planets. We clear that system, and we have our final planetary system. Today I'm really going to be focusing on the protoplanetary disk stage, where the chemistry is really going to be both informing the ultimate planetary system and is also being impacted by the dust evolution that is going to then result in those planets. So I'm really going to focus on the inner 10AU. This is a really important region of the disk. This is the region where we expect that most planets, terrestrial and gas giant, are going to form. So we really want to understand the conditions in the inner 10AU to understand the planets that we're getting out at the end. This region also contains important snow lines, including those from water and CO2. So these are the locations in the disk where it's hot enough for the ices to come off those dust grains and sublimate into the gas phase. And then finally, this is really the connection between the star and the outer disk mass reservoir. And so it's really the bridge in between those two extremes. And we can see a lot of effects from both ends on what's happening in the inner 10AU. So it's a really important region for us to study. So I'll argue here that there are two main drivers of the inner disk chemistry: the stellar luminosity and the dust evolution. So in terms of the stellar luminosity, this is really impacting and really setting the temperature structure of the disk. And as we decrease in stellar luminosity, our snow lines are moving inwards. And that's changing the chemistry, it's changing the time scales of the chemistry in the inner disk. And then the other is dust evolution. As the dust evolves, it's going to have a great impact on the chemistry that we're seeing in the gas. And so one factor that impacts this is the radial drift of these dust grains. As these dust grains migrate and move inward into the inner disk, they're bringing their icy rich mantles into this warm, hot inner region where the ices will sublimate and enrich the gas. On the other hand, we can trap those icy dust grains in the outer disk. If we open a gap, potentially due to a planet, we can keep those especially oxygen-rich ices in the outer disk, leaving an inner disk that is relatively devoid of this emission and is relatively dry. But it's not just the radial distribution of the dust that's important, it's also the vertical distribution of the dust. These dust grains are the main opacity source in the disk, and if you have lots of small dust grains in the disk atmosphere, you can then shield your midplane, the midplane of your disk, from the stellar irradiation. If you settle those dust grains down to the midplane, more of that stellar irradiation can make it to the midplane, impacting the chemistry that we see there. And I'll just note that Andrea and Donnie will really talk a lot about the radial distribution of dust and how that's impacting the chemistry that we're seeing in the next talks. So as Nicole already showed beautifully, this is really probed, this inner 10AU is really probed by the mid-infrared wavelengths. And so it's really crucial that we have this wavelength access to study the inner 10AU. So that takes me to the MINDS survey. This is a GTO program led by Thomas Henning. We have around 50 targets spanning stellar masses and ages. And so we really want to investigate the chemistry happening in the inner 10AU of these disks. And we want to study how this chemistry changes and how the gas evolves from the protoplanetary to the debris disk stage. Over 40 targets have been observed in this program so far, and we see a lot of diversity in the gas and the dust. And so I want to highlight that today. So here is just a snapshot of some of our observations showing the diversity that we see in these Miri spectrum. So here I'm showing the Miri spectrum for these 10 targets where we're looking at the flux versus wavelength, and I'm going from our 5 micron out to around 25 micron where I've cut the spectra off. And we see a great diversity in features. There are disks that are very water-rich, with all of these water features across the whole spectrum. We have carbon-rich, and specifically C2H2-rich disks, which show a really unique chemistry, and I'll just dig into that in a little bit. There's targets that are CO2-rich. They're CO2-rich relative to their water, and that's a really interesting finding. And then we have disks with gaps, where if you open this gap, we're seeing that these disks have less molecular emission, not none, but less molecular emission than their full disk counterparts. So I'll just start here with the CO2-rich source, GW Loop. I'll note that this spectrum is now available on spexodisks.com, so you are welcome to go and see that and download it and play with it yourself. So this is the GW Loop spectrum that we published earlier this year. It has a lot of emission. Compared to the other disks, it may not look like it has a lot of emission, but it does. We see CO, we see water, we see some atomic lines, but really the star of the show is the CO2. So I'll just zoom in on this region here. And this is what we saw with Spitzer in this region, just to highlight where we've come from and where we're going. So here's the Spitzer data, and here's the JWST data in this region. So you can see all of these features here, those are molecular features. Those are not noise. And in the Spitzer data, it was pretty hard to tell whether something was detected or not. And so if we then show the data in black relative to a model, we can see what sort of species are emitting here. So you can see that we're detecting C2H2, HCN, of course the bright CO2 that was seen with Spitzer. We're detecting water, and we're detecting weaker features. And these weaker features, these really small wiggles in the spectra, are where we can get so much science done. And the Miri MRS spectral resolution is really allowing us to detect those faint features that we were not otherwise able to detect, or at least deblend from other features. And so using these features, we can detect 13 CO2 in the disk for the first time, in a disk for the first time. We always thought that it would be there if we had the sensitivity and the spectral resolution to observe it. And then we can also detect these weak features, these hot bands of this molecular emission that can then be used to constrain the gas properties much more accurately. And so, for instance, in GW Loop, we're finding a CO2 column density 1,000 times greater than what was seen in Spitzer when you just use the bright Q branch here. Well, it was all that was observed in Spitzer. So if we then go to our water-rich sources, you can see just this forest of water lines across the whole spectrum. And with JWST Miri, we're able to probe both the row vibrational and the rotational lines. So that's covering a large energy space for these transitions. And Donnie and Andrea will talk about this next, so I won't get into it too much, besides to say that the spectra are beautiful, and there's a lot of water lines here that we can use for our analysis. So I can't talk about mines and I can't talk about disks without talking about PDS-70. This is a really unique system, large gap in this disk, and the only system known to have 2 actively forming protoplanets in the disk. And now because we have the sensitivity and the resolution of Miri, we're able to detect faint, weak water lines in the coming from the very inner disk of this system. So we have this system that is actively forming planets, and now we're able to detect water. Even when you have this huge gap here in this disk, you're still getting water in the very inner system, which is very, very interesting. So I encourage you to see this work from Julia Parati if you haven't already. And then we come to our carbon-rich disks. These are really interesting to me, and I hope that I can convince you of this as well. So we knew from Spitzer that disks around very low mass stars were very carbon-rich. So that was known before, and now I think we're probing that in an even greater sense. So I'm showing here the spectrum from J160532, presented in this paper by Benoit Tabone earlier this year. So this is a very odd spectrum. We see these 2 broad bumps here, and those are being caused by optically thick, very optically thick, C2H2 emission, where we get C2H2 detection column densities of greater than 10 to the 20 per centimeter squared. This is really a unique chemistry and molecular emission that we've not seen before. But it's not just the C2H2. We're also detecting benzene for the first time and other hydrocarbons for the first time in a disk. And it's a really exciting source. But there's no water. And so when you take the C2H2 column density ratio to the water column density ratio, you get a ratio that is 5 orders of magnitude higher than what we would see in other higher mass sources. So something really unique is going on here. But it's not the only spectrum that looks like this. There's other spectra that look very odd and contain even more hydrocarbons. So in these 2 sources alone, we've seen 7 hydrocarbons that we've never seen in disks before. And so this is work that has been submitted and is under review, so please don't take any pictures, but I hope you'll admire it with me. So we'll just go through and watch our molecules waving at us as we go by. So we have all of these hydrocarbons just filling this disk and creating, at such optically thick levels, creating a pseudo-continuum. So we can see benzene here again, waving at us, and we can see all of these other features. And it's a really complex spectrum to then try to deconvolve what all this emission is. So this unique carbon chemistry could be due to a lot of things. Are we seeing the effects of dust settling, and we're just peering closer to the midplane? Are we trapping the dust in the outer disk, and that's affecting the chemistry? Is this just a stellar luminosity effect? We think probably not, but how much is that playing into it? And are we seeing carbon grain destruction? There's so much carbon in the gas that if we're destroying those grains, we can produce carbon in the gas. Or is it some combination? It's likely some combination. But how do we disentangle this? And so really we need to observe more of these disks around low mass stars and brown dwarfs in order to put these into context. Because this is a really unique chemistry, and we really need to understand it better. So I have a cycle 2 program that's going to look at 15 disks around these sources, and we're really going to try to pin this down. So with that, I'll just wrap up here saying we see a stunning diversity of disk spectra and molecular emission and dust features. And it's really reflecting an active chemistry in these inner disks, really dynamic inner disk. But it's really with the power and the spectral resolution of Miri MRS that we're able to zoom into the details of that molecular emission to start to probe the gas properties in much more detail than we've ever been able to do before. And that's really where I think the key science is that we're going to get out of these data. And so on behalf of the MINDS team, thank you.
Thank you very much, Sierra. Those spectra are so rich. I
know.
mean, you can spend years looking at them.
I'm sure we will.
Oh, you will for sure. There is time for 2 questions. Is there anything from online? And let's see in the room. Oh, yeah. Thank you.
Thank you. Naman Bajaj, University of Arizona. I was wondering, you have some spectra which are like very water rich. So are any of those around a very low mass star?
No. None of our very low mass stars, where I'm saying very low mass is around 0.2 solar masses, none of those so far we've detected any water.
So this agrees with low mass stars being carbon rich in general?
Yeah, yeah.
More questions? Yes.
And I guess that goes, sorry, Jaron Lysenring from University of Arizona. So following up, I guess that goes with silicates as well. All right,
in terms of the silicate feature?
Yeah, silicate features. Is that just because they're not there, or they're not thermally emitting, and maybe they're there, but you just don't see them?
If the silicate feature is there, we would see it.
Yeah, okay.
Yeah, that's fair enough. So here I'm showing there's 4 very low mass stars on this plot. So 2 of them, this one here and this one here, they show lots of hydrocarbons, not quite as extreme as the other ones, but they also show the silicate feature. And so that's part of what I think we really need to investigate, is the interplay between what we're seeing in the dust features and what we're seeing in the gas features. Yeah.
Thank you.
Yeah.
Thank you so much, Sierra. I think in the interest of time, let's move to the next talk. But remember, there is a beautiful coffee break and plenty of opportunity to talk. Thank you very much again. Let's thank the speaker again. Thank you, Sierra. And we move to the next talk that will be given by, it's already been introduced by Andrea Banzatti. And let's see if I'm able to get your, yeah, please.
Should be in the folder.
Yeah, it's in the folder,
Right
yes.
there.
There it is.
Should be there.
And is it PowerPoint or?
No, it's a PDF.
PDF, so it should be working, right? So, and now, so the PDF, then we have to move it.
View.
Yeah, but we have to move it here. Otherwise, yeah, and then there we go. And then,
View.
yeah, let me see, view.
Right.
And then
Enter full screen.
and full screen at the bottom.
Right there. Yeah.
Yeah, and you should be fine. And this is the remote. If you want to change the slides, it should be working.
Okay.
Does it? No, I think we have to click on it probably. And now try. Try if it goes. Yes, it does.
Yeah.
I'll give you the 2
Okay.
minutes. Thank you.
All right. All right. Thank you, Sierra, for this great introduction. And thank you for allowing us to present this discovery at this conference. After working for 13 years on this topic, this has been a great joy for me, for us to see this signal finally coming out with JWST. And most of all, I really believe that it's worth having this talk at this conference to celebrate this great observatory. And thank you all for making it possible. So this work that I'm presenting today is part of a larger collaboration. It's not a GTO, it's a collaboration of 3 programs in Cycle 1 with 3 PIs, Pontoppidan, Salik, and myself. We decided to join forces to try to provide the best possible data set with our experience with Spitzer over a decade to the community. Our intention was actually to help the community to prepare for Cycle 2, but the data never arrived before Cycle 2, and so now we are giving the data for Cycle 3. The data is already all public. It's already all there for you to use. And one of the 3 programs led by Colette is a treasury, so there will be also some delivery of tools. Our overarching science goal was the connection between inner disk chemistry and outer disk structure, global disk structures. So a large part of our sample is the D-sharp, the famous D-sharp survey with ALMA, complemented with other disks from other ALMA surveys. The high quality of this data set comes also from the observation of dedicated asteroid calibrators that allow for the highest quality of the reduction of the Miri spectra. These are examples of some of the Miri spectra. And this is really the exceptional work of Klaus Pontoppidan and the vision of Klaus to propose these asteroid calibrators. I will be presenting mostly from these first 2 works, 2 publications from this work. So to better appreciate this discovery, we have to go back in the story. About 4 years ago, solar system studies, and I like to start from this cartoon. It's beautiful in its simplicity and already includes all the key ingredients of the story. First of all, a snow line, the freeze-out sublimation separation between ice and vapor in the disk, and ice drift, bringing in ice from the outer disk inward. So this process was postulated back then to explain fundamental properties observed in the solar system, including the chemical trends in meteorites and the very presence of Jupiter. Fast forward, now we don't, these fast migrators have changed name. They are called pebbles. I'm sure you all have heard of them. And these are pebble accretion and drift is one of the key ingredients of all planet formation models to make planet formation efficient and allow planets to form within disk lifetimes. But we should not forget that these fast migrators are the same that were at the origin of a big issue that we had a while ago, the so-called meter-size barrier. This drift is so efficient that we should have no planets at all and no disks at all because they drift so quickly onto the star. Unless this process is slowed down by something that happens in the disk. And there was this simulation in 2012 proposing that pressure variation in the disk are retaining pebbles in the disk in system of rings. I would like that we all appreciate how visionary this simulation was at that time, because at that time, all we knew is that disks looked like big blobs. This is HL tau in 2011. Until ALMA came online, stunning the world with these sharp images of beautiful rings and gaps everywhere. confirming those predictions. What a joy for the group, Paola Pinilla and collaborators, and for all our community. What a joy and pride now to look back. But ALMA also showed us the full range of disk sizes, from disks that are a few hundred AUs in size all the way to disks that are as compact as just 10 AU or even less in some cases. This has been the intense focus of modeling work recently, and the emerging picture is that while some disks show us that in fact there are these effective pebble traps that are retaining ices in the outer disk, other disks at similar ages instead are drift dominated and are bringing in a lot of these pebbles and ice to the inner disk. Let's introduce the other key ingredient in the story with another unexpected and glorious discovery, now from the Spitzer Space Telescope, showing this forest of molecular lines from tracing water at 1 AU. That's us. Yes, this was a big discovery. But even back then, even on this one, there was a visionary plot that showed us what we were missing, this time from Klaus Pontoppidan, showing us that Spitzer was just not meant to do this. And so all that we were seeing was these subsampled blends of clusters of lines with different energies. And this will turn out to be a key part of my story today, as you will see. But we had all the ingredients in the story. Spitzer showing us water spectra, ALMA showing us the distribution of pebbles and whether they are retained or not in the outer disk. And models proposing that if pebble drift is happening in disks, we should see an enrichment of water vapor in the inner disk in drift-dominated compact disks that have a lot of pebbles bringing in ice, while large structured disks that retain pebbles outside should be relatively water poor. So we were ready at the time to ask this question: is this fundamental process happening in disks, yes or no? And in 2020, we could say, yes, there is a signal in terms of a trend between the water luminosity blended, so observed with Spitzer, and the outer disk radius, as you see here in 2 versions. This was expanding earlier work by Najita et al. And showing these striking correlations between 2 observables that should otherwise be completely unrelated. It's the outer disk radius and it's the inner disk water luminosity. But if pebble drift is really happening, this is what indeed you should expect. Drift-dominated disks should have a lot more water than disks that are retaining pebbles outside. But remember that this was with Spitzer. So at that time, we interpreted in 2020 this effect as a column density difference. And it was kind of a wild guess. And we didn't have really that information because of the lack of the blending of lines. And here comes our hero. In 2023, earlier this year, before we got any disk spectra, I promise, we didn't have any yet at that time, we published a simulation. So this is just a simulation of how much better JWST should have shown us and resolved this forest of molecular lines. And as we all know by now, JWST not only kept its promises, but exceeded across the board. And in fact, as soon as we received the first 4 spectra for my program, those were stunningly beautiful, and we have already seen in Sierra's talk how rich they are. So you may imagine our excitement, my excitement. We jumped on the spectra. We tried to model the whole water spectrum from beginning to end in wavelengths with some of the world experts, John Carr and John Najita, who were the pioneers of the Spitzer detection of water, discovery of water. And we were soon puzzled by finding something that was very unexpected. It seemed that the compact drift-dominated disks were overall colder and the large disks were overall hotter. And really it didn't make any sense because I selected the sample to have similar stellar luminosities. So I wanted to exclude luminosity effects. There was no reason why the disk should have a different temperature in their inner disk. And especially in this way, the compact disk colder, the large disk hotter, it made no sense. We got stuck on this for about 2 months, and we were going into full non-LTE excitation modeling of these spectra, until one morning, I believe, I had an idea. A different question came to mind. And then later in the summer, I heard the talk where there is a perfect quote that describes what happened, and I want to report it here. The right question is what makes the difference. The right question is what allows you to see something that it is right there in front of you, but you could not see before, simply because you were not paying attention. And this is from an Italian chocolate maker. And Fabio, I hope you will see this talk one day, because this is a tribute to now you see, you scientists and chocolate makers, we have something in common. But that's exactly what happens to us. I'm sure many of you know. So the question that came to me was, so these water spectra are very complex, and yet water, while it clusters these lines across wavelengths, it still distributes energy levels at different wavelengths, where hotter water would dominate at shorter wavelengths and colder water at longer wavelengths. So if what we are interested in is something that happens at the eye sublimation front, we should be focusing on the lower energy lines at longer wavelengths, which are also more optically thin. Also, if our science question is, what is the difference between drift-dominated disks and large structured disks? Well, maybe we should just make the difference. So that's what I did. I took the spectra of the large structured disk and the compact disks, I plotted on top of each other, and the answer popped out immediately. The high energy lines are essentially identical in the two disks. And there is, but maybe we could have seen some of it. But I want to highlight that this is the direct outcome of the sharper view of JWST. Okay, so let's summarize what we have learned. While all disks have an inner, hotter, optically thick component, the compact drift-dominated disks have excess cold water that extends all the way to the snow line. And I want to highlight two papers coming out from students that are continuing or expanding the story with more disks, analyzing more disks. Now let me conclude with two telegraphic messages on some exciting implications for this discovery. First of all, with planet formation models proposing that the pebble mass flux entering the snowline region is what determines whether super Earth systems of planets or Earth system of planets, like in this work by Nicole and Lambrex. Imagine if we could use JWST Miri to estimate this mass of pebbles by using the sublimation of ice as a tracer of how much pebble mass has entered the snowline. And connected to that, second comment, imagine of using now determining planets' masses that determine certain gaps at certain location in disks, and in turn, how much water enrichment, how much water you can deliver to the rocky planet formation region. In this, in the most recent paper by Nusha Kalyan, that was the modeling paper of this work, she showed that a Neptune's mass planet at 7 AU would produce only a very leaky gap in comparison to a Jupiter. And that would determine a water rich or water poor and the amount of water that you deliver to the rocky planet region. Now this work is being expanded with a grid of simulations of different planet sizes and how much water you deliver to that region by Whitney Easterwood. She did this work mostly as an undergrad at Texas State, which I think it's amazing, and the paper is in preparation. But all this is really the exciting focus now on many more modeling works. I only list a few here. And now we have JWST giving measurements, finally. And so this brings me back to where I started. Thank you for JWST.
Thank you very much, Andrea. I do not know what is sweeter, chocolate or your spectra. What is sweeter? Chocolate or your spectra?
What is more helpful for society?
Okay, fine.
Chocolate or more spectra?
Really the spectra.
I don't know.
Questions in the room for Andrea. Let's see if there is anything online. I do not see any hand. Oh yeah, I do. Yes, of course you.
Hi, Andrea. Awesome talk. Great spectrum. Gorgeous. So this is kind of, sorry, I'm doing the more, this is more of a comment than a question kind of thing. Mm-hmm. One of the things that got me with Klaus's plot was the R of 50,000 stuff. And it's too bad that Spica got canceled because there was R of 30,000 immersion grading.
That's right.
That would have been an amazing contribution to this type of work to get the radial velocity. Yeah, this one. So you can see at each spectrum, there's a bit of a, each line at the top of R of 50,000, you could resolve the radial velocity lines. And that would be amazing to add to like getting distances, resolve distances for these specific lines, I guess. I don't know if you, sorry, if you this is kind of thing I've been thinking about recently, and it's caught me.
Yeah. If anybody here listening to this talk is now it's related to this topic, yes, we need a space telescope that does this in the future. Next one, please. We can do some of it from the ground, but not at these wavelengths. So we are learning some of that from the ground with high resolution spectroscopy. It's a lot of work that I've done in these 12 years as well. But yeah, having this from space, better than chocolate. For me.
If there is one more quick question in the audience, we really have 30 seconds. But I do, of course, Nicole.
Hi. So, I mean, maybe this is probably a yes or no question. Do you anticipate that there might be other lines that show this extra population in the compact disks? Is that something that you're planning to look at to see if there are other volatile enhancements?
Yeah, this is great. It's one of those exciting implications or follow-ups that I haven't mentioned at the end, but this opens up the question of chemistry, not just water delivery, but more broadly organic chemistry and chemistry in general in the rocky planet-forming region. How does that react to pebble drift, to enrichment or depletion of water, and to gaps that might be in between snow lines? Now here this is focusing on water, but CO2, for instance, would be another great tracer that my colleagues say that we should look at. So CO2, I think, is one of the most promising next. Yeah.
Let's thank Andrea again. Thank you very much for the presentation. And we move on to the next speaker. Please, Danny, come in. And yeah, so let's start your presentation. And so, now I have to find how to, yes, no, I have to move this. Escape, there you go. Heal, go back here. Yes, very good. So, Danny, you will tell us about mind. And is there chocolate or is there water in those mind?
Both.
Both, exactly. Fantastic. Thank you very much. The floor is yours, and this is the remote.
Perfect.
Thank you so much.
All right. Let me see if that works. Okay. Well, first of all, I'll introduce myself. My name is Donnie, and I am a PhD student at KU Leuven, and I would like to thank the organization for, first of all, letting me speak, but also for the amazing sequencing of these talks, because I don't have to do any more introduction, because I think Sierra and Andrea really set the stage very well. So following up on Sierra specifically, I will also be talking about our MINDS disk sample, and then specifically the T Tauri disks, and then related to what we see for the water emission. So first of all, I'm not sure if you're tired of seeing spectra, but I'm not, so I'm going to show one. So again, I think it's really interesting to focus on the fact that the MRS is really allowing us to not just see a lot of detail and give us a lot of sensitivity, but we can see both the row vibrational and the rotational water at the same time. So this here is the spectrum of SZ98, which is one of our more water-rich sources. And before, the only real way to see both of these regions of water at the same time was with the low resolution mode of Spitzer. And I think you can already clearly see it doesn't give us a lot of information. It's mainly just an SED. So if we now really zoom in, we can see the individual lines of the row vibrational water, and we see the individual rotational water. And as Andrea said, this allows us to probe the different levels of excitation, so the different energy lines, and probe much better the temperatures and column densities in the inner disk. So we didn't get here. There's one other thing that I needed to mention. So Sierra also showed us that for CO2, the detection of the isotopolog gives us a lot of unexpected information about the column density related to it being much higher than we thought from Spitzer. So for water, this would be H2 18O.
And this would also help us constrain the column density of water much better, as it is less abundant and it probes deeper into the disk. However, as of this moment, we do not have any detections, but it does give us a nice upper limit on the column density. So here I have a zoom in of the spectrum of SZ98 again, and I'm showing the regular water in blue, and then the isotopolog in pink laid over on the MRS spectrum. And I think it's quite clear that the water detection is super nice and everything overlaps very well with the model, but our isotopolog isn't really detected. But if we kind of figure out how strong or how weak the isotopolog has to be in terms of its column density to kind of be buried into this noise, we can get a nice upper limit on column densities. Spitzer, on the other hand, at the time, I mean, I think Andrea already showed this very nicely, they already identified disk chemistry trends based on what the outer disk looks like. However, they didn't really have this resolution that we have now. So rather than focusing on really the exact column densities, there was more trends related to line fluxes. And these were all blends, of course. So one of the relationships that was previously shown is related to the disk mass, where the more massive your disk, the larger the HCN flux is compared to your water. So you would have a more carbon-rich disk compared to your water. And of course, related to the talk just now, the outer disk radius might be probing this drift inward that would be replenishing the inner disk with water. So what does this look like for our mine sample? Firstly, I need to first just give a definition of what we mean when we talk about radii and gaps in this talk. So this just means a lack of millimeter dust in ALMA, where the outer dust radius is just where this ends at the outer edge of the disk. And then our gaps, they're not the inner part near the star. They are inside the disk, and there's kind of a dip of this millimeter emission in ALMA. And we are specifically talking about, because all of these disks can have multiple gaps, we're specifically talking about the one that's detected most inward and closest to the star. So firstly, this is our sample. Currently, we have 20 out of 33 T Tauri disks detected. They have a range of luminosities, a range of dust radii, from several tens of AU all the way out to 300 AU. That's a very interesting disk. It's very large. And we have a variety of gaps detected here at several radii. And already, these spectra have been normalized with their distance. And just taking a first look, you can already see the large diversity in the different waterline fluxes that we are seeing. So if we measure the waterline fluxes, this is just a blend of line fluxes, so they have different excitation temperatures, but we are already starting to see this trend downwards with the line flux compared to this dust outer radius. And if you plot a couple of these, this is what that looks like in your spectrum. So with decreasing dust radius, these lines are really starting to pop. However, we also see some other disks that are also large, but also have this have a little bit brighter water than you would expect. And we think that this might be due to the influence of gaps. If you have a full disk, the pebble drift is kind of unobstructed. So there's no dust traps, the pebbles can freely drift inward, and you will get a water-rich inner disk. However, if you introduce a gap, the dust is trapped, the pebbles might be blocked, and part of this inner disk would not be replenished in water. And in our sample, we've got such a wide variety of disk morphologies. So SZ98 again here on the left, which has a very close inner gap here. And then, for example, GW loop, where the first detected gap is much farther out. And of course, we've got some with no gaps detected because they're just super compact. So those will not be included in the plot as they have no gaps. So we again look at this blend of line fluxes. Yeah. And we check the same relationship, but this time with the gap. And something that's very interesting is that it seems like, first of all, even disks with a gap can show stronger water emission, but this seems to be mostly, at least for this preliminary plot, this mostly seems to be related to where this gap is located. Yeah, so the farther out the gap, the lower these line fluxes seem to be.
Similarly, now that we have this resolution, we can start to also look specifically at different excitation of the lines. So we're looking at this image here. So if we take a warmer line and a hotter line and take their ratio, we should be probing some of this hotter or cold component that Andrea just showed. So here, I'm just taking a warmer line and a hotter line in a similar region of the spectrum. And this means that the higher this ratio, the larger your cold component or your cold excess would be. And we see a similar trend emerge where the closer in your gap, the larger this ratio is, so the larger your cold component seems to be. So the farther out the gap, the less efficient the drift, question mark. I think this requires more work to further constrain, but I think this is a very interesting trend to look into further. So just specifically to show what lines I'm looking at, so here we've got our favorite extremely large disk again, V1094 SCO, and another larger disk, my favorite SF98. And you can see that with their gap location, you can also clearly see this water going up. And we're specifically looking at this and this line in this case. So this could mean a couple things. Since for modeling results, it seems to suggest that the innermost gap is leading for blocking water enrichment, it could be that closer in gaps are just naturally leakier, that they cannot be as deep as the outer gaps, and that certain grain sizes are just allowed to flow through, still replenishing the inner disk. And this could in turn then be related to the planet size if these gaps are formed by planet formation, so that a planet closer to your star might be less heavy and less efficient at blocking this drift. So just to quickly conclude, this is mainly also a call for myself for future work. First of all, I think we've sufficiently demonstrated throughout this conference that the MRS allows us to see way more individual lines rather than just line blends. The protoplanetary disks in our sample already, and there's many more to come, they are extremely diverse, even when we're just looking at the water emission, and we haven't even started to consider the other molecules specifically related to this story. And the inner disk chemistry depends on the inner and the outer disk structure. So we also need to confirm that with complementary data that we are really looking at the correct morphology and that the resolution of all the observations is the same and uniform. And then depending on the type or the mass of the planet forming, you could have a different depth of gaps, and this in turn will then affect the composition of the disk closer to the star, which could in turn affect the kind of planets forming there. And finally, I think it's also important to note that line fluxes may not be telling the entire story, so we should probably use the improved resolution of the MRS to also look at the column density, as that is a more direct tracer of how much water is exactly present in the inner disk. And with that, I'm going to leave the beautiful faces of the MINDS team on the screen, and I would be happy to take your questions.
Thank you very much, Danny. So, questions, there is definitely time for questions. Is there any question online? No, apparently online people today are not talkative.
It's the last day.
Yes, apparently. Yes.
Maybe it's a naive question, but does the size of the gap matter? Because we see in all those talks the distance of the gap, but what about the size of it?
Yeah, so the size of it and the depth of it, that could be related to how leaky they would be. So if you've got a larger disk, obviously the grains that are going to be able to flow through is going to be, it's going to be less efficient at trapping these pebbles. I think that's the same thing that you would also see for these transition and pre-transition disks, where the gap is essentially, most of the disk is just gone, and there's obviously going to be very little transport there.
And how would it work to have, you say the gap could be moving out, and the further out it moves, the least efficient the drift is. How would that work?
So I think that's something that we need to look into, which is that, because it's not like the gap is drifting, right? You just have a system, the gap is located somewhere. So I guess part of it, because since from modeling, it seems to suggest that if a gap is closer in, it's more efficient at trapping the pebbles.
but it could be that the gaps that are forming closer to the star are just inherently less deep, in which case they would still be less efficient at trapping pebbles. But I think that's something to look into further, because I'm just speculating at this point.
It's a matter of chicken and egg, right? You do not know which one. Okay. There is more time for questions if there is. Oh yeah, Kieran.
Hello, Donnie. I guess I have a sort of more broad question, which is, all of these mines talks and all these disks that we're seeing are low mass star forming regions, and it's really interesting that there's so much water in these disks, and that's usually missing when you look at T Tauri stars in higher mass star forming regions, somewhere like Orion, where that's still quite nearby. So my question is, do you think all of the new amazing things you're learning about these disks apply only to low mass star forming regions, or they really apply to all T Tauri stars?
I think that's a very interesting question, because other trends with star forming region related to the age of the stars and everything as well is something that needs to be explored. So I'm not sure if it's necessarily the mass or the age that we can disentangle there, because especially with the ages, there's often such a wide range, and it's not really constrained, because it is something that I wanted to include, but because it was such a large uncertainty, I chose not to. So yeah, I think, to be honest, that might remain to be seen.
Do you have any plans to look at high mass star forming regions, the most nearby ones, where you could still resolve the disk?
I'm not sure how bright the nearby regions are, and if we are able to observe them very well with JWST. Someone else might have a better idea.
It would be, I think, pushing the limit, yeah. Well, yeah, Olivier might know.
Yes, I can comment on this. It's possible to do it. There are no issues. We just need the TAC to give us time.
Well, cycle 3.
Thank you very much. So let's thank once again, Donnie for a beautiful presentation. Thank you, Donnie. Thank you very much. And we move to the last speaker of the session, John Deeps. Let's see, John, your presentation was already here, right? So, yeah. I think I saw it before. Yes. There it is.
How's my sound? This good?
Good. Very good.
Awesome. I can.
Well.
Great. Thank you so much.
Thank you so much.
Okay. So now for something completely different. I want to thank the organizers for giving me an opportunity to give a talk about first results of a Cycle 2 survey program that has not yet been scheduled any time. But hopefully by the end of this talk, I will convince you that JWST is going to be super awesome for finding planetary systems around white dwarfs, dead stars, degenerates. So I am the co-PI of the Miri excesses around degenerates survey, which is a white dwarf survey for planets and dust around white dwarfs. Sorry to Marjorie DeClaire for stealing her acronym first, or she had it first, most likely. In any case, why do we even care about white dwarfs? These are dead stars. They're just sort of fading away to obscurity. Why do we care, especially for planetary systems? So a year ago, JWST released this very beautiful early release image of the Southern Ring Nebula. And on the left-hand side, you can see the central star of the white dwarf that looks reddish next to its companion A star. And the central star of the planetary nebula is outshining the A star at Miri wavelengths. This is a Miri image, which is weird because it shouldn't be happening. What's happening is even in the early release images, we got a hint of what Webb can do with white dwarfs, which is namely you can see infrared excesses very easily. And there's actually dust around this central planetary nebula star, which I think is cool. When I saw Carl Gurdon talking about this one, that was the first thing that popped into my head was, why is this so bright in the mid-infrared? Now, most stars in the Milky Way turn into white dwarfs at some point in their lifetimes. They're about as common as G stars in local space. So if you're going to look at G stars for Earths, you can also look at white dwarfs for planets. And they tell us something about the future of our own solar system, right? Because our star will turn into a white dwarf. And if we look at planetary systems around other white dwarfs, of which we think there are a fair number, you get some idea about the fate. And it turns out white dwarfs are extremely sensitive probes to different types of planetary systems. In particular, if you take a very nice spectrum of a white dwarf, you can see metal accretion from rocky material at the level of about a 1 kilometer asteroid per year. That's 10 orders of magnitude smaller than than some of these like protoplanetary disk winds that people were talking about. Ooh. Nope, going too fast. Additionally, because white dwarfs are intrinsically low luminosity, they haven't really been studied in the mid-infrared very much. In fact, only a handful of white dwarfs have actually even been detected beyond about 10 microns. So we're in a new era where we can look at a lot of white dwarfs that previously have gone unnoticed and see what we can see. And I should say, in addition to low amounts of rocky material accretion, a few percent of white dwarfs show infrared excesses due to dust that's sort of emitting within the tidal disruption radius of the white dwarf. And so there's something about outer giant planets that are kicking rocky material into the inner system of white dwarfs, and we see this about 25 to 50% of the time, some kind of accretion, and a few percent of the time where there's active dust emitting. So while I won't be able to really tell you much about some of the cycle 1 and 2 geo programs that are ongoing, including MEAD, there's also the MEOW survey by Marianne Limbach, and I should say with deep Miri imaging. We went very deep at 15 microns to look for direct imaging of giant planets, cold giant planets, but we also took 3 other filters with shallower images at 5 microns, 7 microns, and 21 microns to also characterize the long wavelength tail of the white dwarf SED to look for infrared excesses. So I'm showing here the initial results for our first target. This is a paper being led by Sabrina. This is WD2149, a Cal-spec HST star that is otherwise fairly unremarkable. This is the image at 5 microns of the white dwarf. You can see it's getting fainter as you get to 15 microns. And then what we did is just straight up direct imaging, so we get photometry of the white dwarf, but we can also do reference PSF subtraction. You can see we can do a pretty good job. Especially at longer wavelengths, we get down basically to the background limit very, very quickly of a 6-hour integration. So Sabrina has created these very nice contrast curves that we get as a function of projected separation for this particular white dwarf. And you can see with these direct imaging, we get contrast ratios of like 10 to the minus 3, which is modest, but we don't need a lot of contrast to start probing to planetary mass objects. Our sensitivities are a fraction of a Jupiter mass to maybe a few Jupiter masses, depending on what models you prefer. And just for fun, we scaled Jupiter to 22.4 parsecs, and we wouldn't have detected Jupiter. But 2149 is younger, so a Jupiter analog would actually be a little bit brighter. And of course, a lot of the models we're using don't have clouds or some of the more sophisticated chemistry, which may change what we're actually sensitive to. But we're also sensitive to dust. So we looked at the photometry of the long wavelengths. The absolute flux calibration is good to about 5% right now. And we didn't see any excesses more than what we would say is significant. So that limits the amount of dust that must be in orbit around the white dwarf. So I don't have time to go through the details of this, so you can ask me about this afterward. But we have observed 2149 to be accreting for at least 14 years. So we know that there must be at least about 10 to the 16 grams of something around the star. And these are our mass limits under some assumptions of what kind of dust may have been emitting and the fact that we didn't detect anything. And then there are models that predict how much mass should be around a white dwarf that has a certain accretion rate. And those are given by the solid lines for the total mass. And if there's a collisional distribution of dust, we would maybe see about this much mass that's emitting around our white dwarf in the infrared, because large bodies you can't do very much with. So we are getting to the point where our mass limits are going to start constraining models for a wide variety of accreting white dwarfs. As I said, this particular one is a pretty low accretion rate white dwarf, and there are many that are orders of magnitude more massive that have no infrared excesses. keep pressing the wrong buttons. So we can put all the sensitivities to planets, both unresolved and resolved. We can compare them to what was done in the past. So for my thesis, I used a combination of Hubble imaging and infrared excesses to limit planets, and Susan did the same with Spitzer. So if you took 2149 and you just took the limits of both direct imaging and infrared excesses, this is what we could do in the mid-2000s. With JWST, we're about 40 times better, right? And I've also overplotted as a function of semi-major axis and mass all the known exoplanets that have been discovered by various techniques. And you'll notice that our parameter space pushes into very interesting areas. And you'll notice two different colors. One is black for planets that probably won't survive post-main sequence evolution, and blue planets that probably would, right? And then it gets better. If you survive and don't tidally interact with your giant star, you move out. And so we actually have additional sensitivity because of that. So we are in a regime where Webb can potentially, for a large enough white dwarf sample, start probing planet occurrence rates in an interesting way. So, you know, if the TAC wants to give me 500 hours to look at the 200 nearest white dwarfs, 6 hours a shot, and then come back to the ones where we find candidates, great. I'll also point out that we have 2 candidates already out of 4. We think, so these are both point sources. We subtracted off a scaled down version of a point source PSF to verify that we're not seeing anything extended for these 2 objects. They're red. And so we have also, from our Miri fields, estimate that we have about a 2% chance of getting something this close and a point source. Most sources in a Miri field are actually resolved. So that's a ray of hope that we might be on the right track to finding some cold giant planets. We need to follow this up with common proper motion to be sure. And Susan's poster talks more about it. Okay, in the last minute or 2, great. I can talk about the survey that will happen any day now, as soon as there are gaps in the long-range plan. But the 25 parsec white dwarf sample spans a wide range of temperature, mass, and it's about 220 single white dwarfs that we're going to look at. And then we're just going to have really great sensitivity, just as I showed in the earlier plots, both to planetary companions and to dust. So we're focusing at 10 and 15 microns. 10 microns is for very sensitive silicate emission features. 15 microns is for planets. And of course, both give you something about infrared excesses. So down to very cool companion limits, but also very low dust limits. And things are relatively flat across our temperature range, which is great. The only downside is that the cooler white dwarfs tend to have much older planets. Okay, so JWST will find and characterize planetary systems around white dwarfs. I guarantee it. And it really improves our ability to find planets that should exist, and by like a lot. And just remember, we are sensitive to like very low levels of dust. It's just really exciting. And hopefully, with a lot of new surveys, we'll find really great and interesting things. Thank you.
Thank you very much, John. I guess that with a request for 500 hours of JWST time, the TAC will ask you quite a number of questions. Let's see if there are a few questions in the room that can prepare you.
You're right.
Questions? Yes, please.
What fraction of a known white dwarf have an infrared excess at 20 or 10 micron?
Unknown. We've only looked at a handful beyond 5 or 6. So from Spitzer, right, where we're like sensitive to things at like 3 and 4 microns, it's a few percent. But it's presumably a luminosity distribution, right? And so Spitzer was primarily sensitive to things that were accreting at a level about 100 to 1,000 times more than 2149. But with JWST, we should catch almost things down to that accretion rate. So there should be a whole lot more subtle, very low-level infrared excesses that exist that now should pop up with Webb. In theory, any white dwarf that's accreting material has an infrared excess, but some of them it's like 10 to the minus 5. You'll never see it.
Are there more questions for John? Maybe from online?
Yeah, there's one online from Zhongyi Ro. What is the origin of the dust at the center of the nebula? Don't know if that's.
Oh, so the planetary nebula, right. So this is not my work, so I just quickly read a paper, but basically what it looks like is, in that particular case, the central star of the planetary nebula has a 50 to 100 AU dust disk that's being lit up by the central star. And so when, at the planetary nebula phase, the luminosity of the proto-white dwarf is quite large, and so you're going to light up dust very far away. But for these cooler white dwarfs, which are like 1,000th the luminosity of the sun, you really only light up the dust that's most close by to it. So the origin of that dust is unclear at this point. Could be just like your Kuiper belt lighting up and kind of disintegrating it from the luminosity of the central star.
Okay, let's thank John and
enjoy your coffee.
And I think now we have a break for coffee, and we resume in 3:30, right? For the final session on dusty galaxies. Thank you.
Recording has stopped.